Yeah, this building is cool because it's a building that perfectly is height much higher than ground. Get the front view of that room. What's the matter? So it's like, guys, sure, good thing you're on the 8th floor. Not yeah. Or actually, maybe you want to be higher. Yeah, the height, of these rods you do from a rod are twice the height of the fish. Very difficult. The downside is there's still parking garage. City doesn't like it. No, it's that the first 3 floors of computer science. Yeah. Hello. Everybody. So we get started? Can everyone hear me? It's on. All right. Okay. Hello. I'm very excited to welcome Kate Sanka. Kate's our second keynote speaker for WACV. Kate's a professor of computer science at Boston University, where she leads the computer vision and learning group. She received a PhD from MIT and did postdoctoral work at UC Berkeley and Harvard University. She's best known for her seminal work on domain adaptation and dataset bias, as well as early vision and language work on video captioning and visual question answering. Welcome, Kate. Thanks for joining us.
Hi, everyone. Thank you for the introduction, and thanks to the organizers for inviting me to beautiful Hawaii. Very excited to be here, and let's get started. So I want to talk about this domain gap issue, and I want to start with an anecdote. When my youngest child was 9 months old, we used to read books, and there were a lot of books about dogs. And every time I would see a dog in a book, I would make the dog barking sound, you know, like you do with babies. And so he didn't really talk yet, but he could consistently make the dog barking sound, so I knew he recognized dogs. But he's never seen a real dog. We didn't have a pet, we didn't have any dogs. And then one day, we were out on a walk in the woods by our house, and we saw a real dog. And my son started making the barking sound. That means he actually recognized that this was a dog. And to me, this was really amazing for a couple of reasons. I mean, as a new parent, of course, but I realized that, okay, so babies can do where they've learned about a category purely from these very simple drawings, depictions of a dog, and then can recognize the real dog in a very different lighting, very high degree of realism, different viewpoint, everything is so different here. And the reason that I was so shocked is that I knew that computers can't do this. Our AI models, even back then, I already saw this problem where if you train models on, let's say, drawings of a dog, it will not be able to recognize a real photo of a dog, at least not well. So that's kind of this problem that has been motivating a lot of my research, and it's just mostly what I want to talk about today. So I'll start by defining this issue of distribution bias, and then we'll talk about why it's a problem for deep learning methods today still, and some solutions, and then we'll also look at the role of pre-training, so not just solutions after pre-training, but also during pre-training, or how pre-training affects generalization to this kind of new data that's out of training domain. And finally, I want to talk about maybe we can fake pre-training, meaning that maybe we don't have data that's suitable for a downstream task that we can collect from the web, but we can maybe get around that by faking or simulating the pre-training data and see how well that works. All right, so let's start with the problem itself. So the problem of distribution bias, it's also known as data set bias, domain shift, many different terms for it. Essentially, is this problem that what your AI is trained on is different from what it's tested on. This happens all the time in the real world, as I'm sure many of you have come across this problem. I first came across the problem when I was training an object classifier on some Amazon images of products like cups and other objects. It was getting very good accuracy of 90%. But then when we applied this, the same model to some new data that was collected from a mobile robot, the accuracy dropped a lot, more than 20%. So that's bad. And what is the specific nature of this domain shift here? Well, there's this web kind of data that has white backgrounds at training time. There was different backgrounds, different viewpoints. Oops. And we have catastrophic domain shift to nothing. Oh, no. We have something on the sides. Okay, I'll just keep going. Right, so there's backgrounds, there's viewpoint differences, there's kind of this web data to real data shift. Now, okay, great. Another kind of domain shift causing factor could be geography, right? So here we're training an object detector for a self-driving car on data collected, let's say in California. And then when we run it on data from New England, where I live, we have snow, we have people wearing heavy clothes. Again, the kind of visual appearance of pedestrians can be quite different. And in addition to geography here, we also have season change, right? So it could even be more extreme, like rainy or foggy. And this is something that even humans can have trouble with, of course, if the image is quite degraded from fog, for example. But speaking of seasonal change, here's another example from a real world application. So what we're doing here is we're trying to recognize different kinds of recycling items and sort them using robots instead of humans. So we're distinguishing between cardboard and plastic and paper. And so this is from a data set called Zero Waste that we just recently released. And season makes a difference here because the kinds of recycling that hopefully we all recycle, right? So when we take our recycling to the curb, it can be very influenced by seasons. So we just had the holidays in the US, and of course there's lots of wrapping paper and things like that. So the stream of recycling will look fairly festive right after the holidays. And in general, it's affected by seasonality. So that's another example. An even more extreme kind of shift is from simulation to real data. And this is very relevant in robotics applications, of course, where we sometimes cannot even train in real data because it's expensive or we might break the robot. And so we need our models to be able to handle this kind of sim to real shift. And then another example is the shift from different demographics. So this is a famous example where face recognition models are not as good at faces that are have darker skin or female faces compared to lighter skin and male faces. And this is also due to a bias in the training data, where the training data has, it's biased towards these kinds of faces. And so the model doesn't work as well. Okay, so gender and race can be causes, kind of giving you a bunch of different examples, and this is not going to be an exhaustive list by any means, but just kind of to give you an idea. Okay, another one is style, or what I refer to as style. So essentially, real photos versus paintings, or clip art, or drawings, or even very simple sketches, right? So if you're training on ImageNet or roughly kind of real images of objects, and then you want your model to work well on drawings or clip art or more paintings and other kinds of objects. So this is a style-based change. And then finally, here is one that I put question marks here because I'm still puzzled by what is causing this domain shift. So this is from a paper called Do ImageNet Classifiers Generalize to ImageNet, where they essentially just collected another version of the ImageNet test set, called it ImageNet v2. They use the same exact collection method. It just happened later on, so should be the same distribution, but it's not, because as you can see, there's the model will have much lower performance. This is very big shift, a very big drop in performance rather. And so definitely the distribution of the test data in V2 is different from test data in V1, but it's not obvious just by looking at it what causes this extreme shift. All right, so I've shown you a bunch of examples. As I said, not an exhaustive list of things that could cause it, but let's now talk about why it's a problem, right? Why it's a problem for modern methods that we use. We all know very well deep learning methods. Well, I think that one of the reasons that this is such a problem is, first of all, we don't test for it, right? So if you think about it, the vast majority of data sets out there have IID test sets, right? So you collect some data, and then you sample a training set, and then you sample a test set, identically distributed. You train on that training set, and you test on the IID test set, and then you declare victory, right? But this really overestimates the generalization of the model, right? Because again, you're testing it on the exact same distribution of data that you train the model on. But nevertheless, 99% of all papers in machine learning are doing this. And what I think is a better approach is to evaluate models on out of distribution data, right? And at the very least, this will expose this problem more, and hopefully will expose the true generalization error of a new model that we're developing, as opposed to kind of ideal improvement that we're seeing on an IID test set, right? So what we could do is, for example, train on one or several training domains. So here I have rain, sunny and foggy data, for example, and then test the model on a completely unseen domain, let's say snowy data. And so this is called generalization, where the model cannot train on this new distribution. It just has to be tested on it. It has to work well. An alternative setup is when we have some data from the target distribution, which is mostly unlabeled or all unlabeled, and the model needs to adapt to it quickly and efficiently. So that's domain adaptation. All right, so you might be thinking, wait, but we can solve this, right? Like we can just collect some more representative data and label it, and we'll fix the problem. Well, yes, and in some cases that is a perfectly good solution. But in many other cases, and I would argue in general, it's going to be very difficult to exhaustively label everything in the world that you care about or your application cares about, right? For real world applications where you really need to handle a lot of different kinds of inputs, this is going to be extremely costly and time consuming. In addition to cost and time, there's also situations where the data stream is shifting continuously, for example, in social media. And you may not even have time to collect data, label it, retrain your model, and redeploy it all the time. Also, some of the labels might have a long tail distribution, and it just might be hard to even find examples of those labels because they're so rare, and you might have trouble just collecting enough training data for your model. So instead, the philosophy that I subscribe to and that a lot of other folks subscribe to is that domain shift happens. Let's just deal with it. And let's deal with it by building something into our training algorithms, into our AI models, that it's kind of like the baby in my earlier example, right? Can learn to map between different visual appearances of objects and understand that there's some underlying structure that is similar and not kind of overfit to a specific training data, but kind of learn to generalize to new appearances and shifts due to all of these kind of factors that I talked about. All right, so let's dig a little bit more into this problem. So why do deep learning methods in particular have lower accuracy? Of course, it's not unique to deep learning, but that's what we use these days. So one of the things that we know, of course, is deep learning methods learn hierarchical feature representations from data, right? That's why they're so good at what, they have high performance, because they learn good features. But they learn the features from the training data, right? So they're only as good as the training data they're given. For example, if here we have a network that learns some hierarchical feature representation of edges and then parts and then whole faces, perhaps. If this model is trained on only adult faces, it will learn features that are useful for representing adult faces. And then, of course, if we give it inputs from a new distribution that has babies' faces, it will have poor accuracy because it hasn't learned features that fit the baby's face, right? The babies have a different proportion, they have bigger eyes, bigger foreheads, so the kinds of features the model learned on the adult face data set will not generalize well. And you can see that here, right? So again, more specifically, there's these two problems here. One is that the train and test distributions are different. So here I'm showing you a distribution of the training points in blue, and the new distribution, the target domain as we call it, is red. And you can see, of course, clearly that the two distributions are very different. Even though the underlying class labels are the same, it's the same problem. And the other thing you notice is that the model trained on the blue data is more discriminative on the blue data than on the red data, right? So you see the blue points are much better separated into clusters, so there are 10 different digit classes in this example. Whereas the red data, there's also the same 10 digit classes, but they're much more mushed together and not as well separated. So the features are not as discriminative on the target domain. And so we know from theoretical results that this is a well-known kind of model of this phenomenon theoretically, that our target error, so that's this epsilon t of hypothesis H, so that's the error of the hypothesis on the target data. This is bounded by these terms. So we have the error on the source of the hypothesis plus this term D, which is a divergence or difference between the domains, the distributions in the source and the target domain, plus this last term, which is essentially the difference between the labeling functions in the source and the target. And so that last term, we expect it to be small. We expect the labeling functions to be very similar. And so the problem really is the second term. In fact, usually it's expected that the error on the source is low as well because we have training data on the source. So then the real problem becomes the second term, which is the divergence between the distributions. All right, so here, this is the technical definition and this result of what the divergence is. But in practice, we can define other types of divergences, right? So as long as it's a divergence or some measure of the difference between the two distributions, what this result tells us is if we can reduce that difference, then we at least have lowered our upper bound on the error, right? And, this shouldn't be taken as, okay, we're always going to have higher error whenever the distributions are different, but there's just more room for higher error, right? So it's just an upper bound. All right, so if we can do that, maybe we can use that insight as a part of a solution. So the first solution that I'll talk about, and this is something that's fairly widespread and well known, is just kind of, if you are not familiar with the area of work You may not realize this, but if you are, it's pretty well known. So we have some source data with labels. We have a network that generates features, and then some classifier layer that predicts the classifier labels, and we can train it with classifier laws. And that classifier layer will learn some decision boundary in feature space. Now, we also have unlabeled target data and domain adaptation. And if we extract features using the same network, so the orange features are extracted from the unlabeled target distribution, and as you can see, they'll have a different distribution. And this will cause the classifier to fail or to have a higher error. Okay, so again, the problem here is that feature distributions are different. So the first solution will be to try to align the distributions. And in fact, the alignment will be an adversarial alignment. So we introduce a domain discriminator whose job it is to distinguish the two domains, right? So it's trying to predict the domain label of these features. Okay, and at the same time, we're also alternating that with an adversarial step of maximizing the error of this domain discriminator. So ideally, if everything converges, the two domains, the features will become indistinguishable in terms of their distribution, and the domain discriminator will have high error, right? So it will not be able to tell the two distributions apart. Okay, and this works quite well under certain assumptions. Right? But there are some problems with this idea as well. So, there are a couple that I listed here, like mode collapse. This is similar to GANs, and as we know, in GANs, we have this problem. There's also no guarantee that the distributions will be aligned, even if the domain discriminator has very high error or has zero accuracy. The full alignment that is trying to do here also may not be necessary, or may even be a bad idea. For example, if our target domain has novel classes, then we don't want to do the strict full alignment. But the one I want to focus on is that the problem here is that this alignment is not using the classifier. It's not using the decision boundary at all, right? It's only conditioned on the feature representation. So to fix this, this paper from 2018 called Conditional Domain Adversarial Network, or CDAN, what they did was they said, okay, let's also condition the domain discriminator on the classifier's output, right? So the distribution over the labels is now also fed into the domain discriminator in addition to the feature itself. And so this does improve the ability of this alignment process to kind of fully align the two domains. It tends to give better results. And in fact, I'll come back to this method a little bit later. Okay. So I talked about feature-based alignment, feature space alignment. The second idea that is fairly prominent in this line of work is pixel space alignment. And the idea is, okay, why don't we actually align at the pixel level, which means let's take our source data and use something like a GAN perhaps to translate those images directly to the target distribution of images. So at the pixel level, right? So we're going to make the images themselves look like they come from the target domain. And so as you can see here in this example, which is from 2018, it's not the greatest result, but you can see that what the GAN is trying to do is maybe add something to the background of the source data to fix the problem here, which is that the source data has white background and the target data has non-white background. And so this method also works fairly well depending on the kind of data you have. And as you can imagine, the easier your data is to align in pixel space, the better this will work. All right, but this was a while ago. Maybe we can do better in 2022 than we could in 2018. And also, what about larger shifts? So for example, can we align sketches and real photos? So that's the subject of this next paper that I want to talk about, called Mask Sketch. Mask Sketch, unpaired structure guided masked image generation. So this is led by my student Dina Bashkirova, who is also here in the audience. So if you want to talk to her about this, feel free to ask her. And she's also graduating soon, so on the job market. So the idea here is how can we take a sketch or some other style image, but we're going to focus on sketches, and then translate it to make it look like a real photo. Right, so the model is going to get the class label, in this case volcano, because we're in Hawaii, so why not? Let's try it. All right, and then here's the output. Okay, so that's what we want to do. We want to take a sketch and translate it to real photo. And compared to other text conditional generation models that, of course, you know, many of you have seen that have been making a lot of headlines, they're given some label or perhaps a caption, so volcano or photovolcano, and then they generate images, and the images look quite realistic. So the difference from that to what we're doing here is that we have a label and a sketch as input. So the model needs to generate something that restricted to what the sketch provides. And in general, if it's not a sketch, maybe it's clip art or something else, we want the generated image to follow the structure of the input image. Okay. So this approach that we're taking is based on a model called MassGit, which was presented at CVPR this year, and it's state of the art for image generation. And it's based on quantized visual token representation of an image, right? So there's an encoder that maps an image to visual tokens, and then a decoder that reconstructs the image from those tokens. And then to generate an image, MassGit uses this mass token iterative sampling, right? So we start with everything being masked, and then we predict a few of the tokens, and then we feed that into the next step, and then we sample more tokens, and we keep going until the tokens are sampled to the degree where the reconstructed image looks realistic. So one thing that is interesting about MassGit is that it has this self-attention. And the self-attention, turns out, preserves the structure, or it encodes the structure of the object in the image. Right, so what you see here is the PCA map of self-attention of the MassGit model, and you can see that both for real images and for sketches, so very different styles of images. But despite the difference in style, the self-attention PCA clearly encodes the structure of the object. And so the key idea in our method is to make use of this in order to generate a real image that has the same structure as the input sketch image. Okay, so going back to regular MassGit sampling, we have some mass tokens that are black, and then some that have been sampled that are in color. We sample more tokens at each step, right, based on the confidence of the token. Right, so here we've generated a bunch of potential tokens, and we just took a couple that were higher confidence for the next step. That's the regular process. The difference from that to our approach is that the tokens are now sampled also based on their self-attention similarity to the guide sketch image. Right, so down here in the bottom, you can see the guide sketch image and its self-attention. And then when the tokens are sampled, their self-attention is also compared to that guide self-attention. And then they get sampled only if their similarity is sufficiently high to the structure of the sketch image. So let's look at some results. Here we have some sketches or sketch-like images or drawings in the top as input. And then the second row is the resulting photo that's generated by our model. And you can see here that these inputs range from very simplistic drawings to flip art to some very detailed drawings. There's another 2 rows of results at the bottom. So it works quite well. In fact, we compared it to quite a few existing methods for sketch to photo translation, and this approach worked quite a bit better. The one downside of it is maybe you notice by looking at these examples is that it doesn't always fully follow the structure of the sketch. Maybe you can see that, in like looking at this mushroom on the bottom right. So the shape of the mushroom that's generated, the real photo is not exactly the same as the shape of the input sketch of the mushroom or drawing of the mushroom. But still, it works remarkably well and remarkably better than existing approaches for this problem. So the point is that, we have a lot of advances in generative AI that I think and I hope we can use in order to bridge this domain gap even more as we keep going. And speaking of bridging the domain, so I want to mention another idea, which is, okay, now instead of aligning kind of source pixels to target pixels, where we're trying to match the style of the target, why not just strip away all the style information from both source and target? And maybe now we have multiple domains, so we don't just have two source and target domains, we just have a bunch of different domains. And maybe we can strip away all of the style and kind of translate them to this bridge domain, which just preserves the outlines or the structure, the edge structure of the object. And then we can kind of do training in this bridge domain where we train the model to learn the features, but when we find let's say we use self-supervised learning, instead of finding neighbors in original pixel space, we're going to find neighbors in this bridge domain space. And the point of that is that we want the contrastive learning to find neighbors that are similar in terms of their outline or their structure and their object label, hopefully, and not similar in terms of their style. Because we don't want the model to learn to rely on style. So this is the idea in this paper called Unsupervised Domain Generalization by Learning a Bridge Across Domains. That was presented at CVPR this year and is a collaboration with lots of people. So again, the idea here is that we have a bunch of different domains like paintings, real photos, we have some clip art, some sketches, and we're going to learn to map them into this bridge domain. We call it BRAD, which stands for bridge domain. And this domain is somewhat like edges, but it's not exactly edges, it's learned. It's initialized with edges, but then after that, it's just learned. And I'll show you a better visualization of what it learns. And then once mapped into this domain, this is where contrastive learning finds the neighbors and the different pairs. So the idea is that we want to align a picture of a painting of a giraffe to a clip art of a giraffe and not to another painting because the painting style is similar, right? So we want to strip away that style of the image and just preserve the object features. So here's the visualization on the left hand side is the original image. The second column is just a canny edge detector. So as you can see, it extracts all edges, including all the noise that is not relevant to the object. The third column is the HED. It's a learned edge detector, and it tries to only extract edges that are relevant to the object outline. As you can see, it does a much better job than a regular canny edge detector. And then in the last column is our bridge domain that is learned. And as you can see, the difference here is that in our bridge domain, the giraffe still has spots on it, whereas the HED edge detector has lost these spots. So, this is important because it's important for the identity of that class, right? The giraffe has spots in its neck. And similarly, this house, you can see that in our version of this bridge domain, maybe it's hard to see because it's so small. I apologize for that. But the windows are preserved in the bridge domain and they're not preserved in the edge extractor. Okay, so again, the idea is to kind of strip away all this style related stuff and just learn how objects can match just based on these outlines. And maybe that's something like that humans do or babies do. Maybe, there's some underlying structural representation that they use to kind of relate objects that are the same object, but are appearing in different styles and different appearances. Okay, so I talked about a couple of approaches to kind of domain adaptation, domain generalization, but I want to switch gears a little bit and now talk about what happens at the pre-training stage, because in all of these methods that I described and all of the vast majority of the methods that you read about in the literature, the adaptation and generalization method works after the pre-training stage, right? So you have some pre-trained model, usually it's ResNet, pre-trained on ImageNet 1K, and then you start training it on your source data and adapting it to your target data. But we're living now in this era of the supersized model, right? So in NLP, of course, the size of models has increased dramatically over the past few years from 2018 to this year, now 2023. And I don't know if it's a coincidence or maybe you noticed that the names of these models went from something fairly cute like Elmo and Bert to something downright menacing like Megatron. I don't know if that's a coincidence. And then in computer vision, of course, we're not quite there yet at the same scale of model size, but we're catching up. So Flamingo has 80 billion parameters in it. Self-supervised learning is also increasing in terms of size. So the Seer model goes up to 1 billion parameters. So we're getting there. And so one of the things that I've been wondering about recently is maybe when we scale up our pre-trained model, maybe it starts to behave differently in terms of domain generalization. And in fact, something happened last year when we were running our annual domain adaptation challenge. We posed this adaptation problem where the source domain was ImageNet and the target domain was essentially sketches and different viewpoints of the same objects, different kind of angles on those objects from this ObjectNet data set, and also some missing objects as well. And we thought, okay, this is a great challenge for the community to come up with a better domain adaptation method that can handle all of the stuff. And we got our results. This is the leaderboard, and we noticed that the top team, the winners, got a much higher accuracy than the second runner-up, which is if you participate in competitions, that's pretty rare. Usually the top and the second runner-up will be fairly similar. But here there was 56 versus 49, so a pretty big difference. And then when we looked at their solution, we realized that the winner actually didn't use any adaptation. So, we were kind of puzzled by this. They didn't use domain alignment, they didn't use adversarial alignment or semi-supervised techniques or anything like that. What they did though was they used a transformer. And now this is late 2021. Transformers had just kind of come out in a big way. And they used something called BEIT or BERT pre-training of image transformers. And so we thought, maybe there's something to this. Maybe there's something about this architecture that now just generalizes so much better than before. Or maybe it's the fact that, their model is much bigger, right? Because this model was, in terms of the model size itself, much bigger than all the ResNet models that we were using. So we wanted to look into this more. And so we ended up publishing this paper that was presented at ECCV this year called A Broad Study of Pre-Training for Domain Generalization and Adaptation. This was led by my former student, Dong-Yoon Kim. And here, what we wanted to look at is, again, the pre-training step, right? So before we train the model on some source domains and then test it on some new distribution and maybe apply some domain shift methods here or domain adaptation methods, even before that, what happens if we change things at the pre-training stage? And what we wanted to look at is changing the architecture, so comparing a convolutional network to a transformer, changing the depth of the network, or essentially the size, the number of parameters, changing the data sets that we're pre-training on. What happened when we pre-train on a larger data set like ImageNet 22K or GFT, or even the CLIP data set, which is 400 million of photos and captions, and also compare self and supervised pre-training methods. Right, so the setup is as follows. We pre-train the model using all of these things that I just described and varying them. And then we take that model and we fine-tune it on the training domain or training domains in the case of multiple domains. And we measure its accuracy on a held out test domain. And then here I'm showing you 3 of our data sets. So CUB or CUB, this is fine-grained bird classes. And there are different domains here, like these white backgrounds and sketches versus real photos. And then DomainNet has 6 different domains and 350 classes. Wilds is a data set that has different wildlife cameras in different locations. So the different domains are different locations of the cameras. And so just to kind of cut to the chase, do pre-training and backbone matter in terms of generalization? Yes, they matter a lot. So here I'm showing you the accuracy of various domain adaptation methods. You know, they don't all work well, but some of these are state-of-the-art and they work pretty well. And then here is the accuracy of no domain adaptation, but just swapping the backbone. Instead of ResNet 101, which all these methods use, here we're using ConvNext extra large. So it's a different convolutional network. It's a more modern convolutional network. And you can see that even starting with that and no extra adaptation method or anything, it already beats all of these by a large margin. So we sort of reproduced that result that I showed you from that leaderboard that kind of puzzled us, right? Even though this is not even that same model, that's not the transformer. Here, this is convex. Okay, the next question, and I'll go fairly quickly here, but welcome to look at the paper, of course, for more details. So next question is, does the model size better? So here we are keeping the model the same, but we're increasing the number of parameters. And in general, the answer is yes, bigger is better, right? So the bigger the model, the better the generalization will be on new domains. And this holds up across different data sets, across different models, CNNs and transformers. What about the architecture? So here the story is more muddled, actually. So on average, so what we're doing here is we're comparing different backbones, starting with ResNet 50, which is fairly standard in domain adaptation. And then we compare it to ConvNext, to DIT and SWIN transformer. And we're pre-training all of it on ImageNet 1K here. So just to keep everything else consistent, same pre-training and same number of parameters or very similar. And it seems like on some of these data sets, the transformer actually does better, like in CUB, that fine-grained bird data set, transformer does better. But on DomainNet, that 6 domain, more of a web kind of data set of basic categories, the CNN does better. On average, the transformers do a little bit better than CNN, but it's clearly not a consistent story depending on what the downstream task is. So I think this needs quite a bit more research. One thing that is very clear, though, is that both ConvNext and DIT and SWIN are much better than ResNet 50. So here it's a pretty clear improvement. And that's at the same size and the same pre-training data. So just like changing the architecture really helps with generalization here. All right, what about the pre-training data set? And here again, generally, the bigger the pre-training data set, the better generalization you'll have. For example, pre-training, switching from ImageNet 1K to ImageNet 22K, you get a big boost. So that goes from blue to red. Blue is ImageNet 1K and red is ImageNet 22K. Both for SWIN-B and ConvNext, you will see this big boost. Not equally large though on all the data sets. But if you look at the bottom right, so here we have the effect of adding images with captions to pre-training. And so here, this is CLIP. So you're pre-training on 400 million image caption pairs. And even though it helps a lot on some of the data sets, but not on all. So you can see again on CUB, it actually hurts performance, right? So it hurts generalization. But if you look at domain net, it goes up a lot, 15.7%. So it's interesting because, you know, in general, it seems like more pre-training data does give you better generalization, but that's not consistent across all downstream tasks. And there's something about this pub data set that we should look more into. All right, so finally, this is a question that I'm most worried about. What about domain adaptation? Do we still need it? Maybe we don't. Maybe we just do this kind of huge pre-training and we're done. And the answer here is interesting again, because yes, it does help, but turns out that older methods work better than more recent state-of-the-art methods when you switch that backbone to be the more modern backbone. And in particular, if you remember the conditional domain adversarial network, the CDAN method that I talked about earlier from 2018 is actually the one that works the best. And so my takeaway from this is that as a community, we should be careful that we're not over-tuning our methods to older architectures and older, less modern ways of pre-training, because clearly there's something that happens at the pre-training stage that's very important to generalization. We shouldn't be ignoring that. Okay. So far we sort of talked about, all these data set shifts that, more or less all the results I've shown you were for objects, right? Like dogs, cats, and so on. But what about other types of tasks or downstream applications that are not very web-like or not, for the data that is hard to find on the web? Is pre-training on web data still the right thing to do for these applications, right? So I'm talking about things like, for example, medical images, like chest x-rays, sketches. You can definitely find sketches on the web, but it's just further away from ImageNet than photos. Also, this kind of example of fine-grained categorization, maybe the flowers or other botanical data sets where we have to make fine-grained distinctions between different species, satellite images. All of these are examples of data that is hard to come by online. And so the question is, should we still use online data like ImageNet to pre-train for these tasks? Or maybe we can do better, and maybe we can even fake the data or generate custom pre-training data that can improve performance on these downstream tasks. And so that's the last thing that I want to talk about in my talk is like, how can we get better pre-training data, potentially just by faking it with simulation. So this is from a paper called Task to Sim that was presented at CDPR this year, and it's led by a PhD student of mine, Samarth Mishra, in collaboration with the MIT, IBM, Watson AI Lab, and Cornell. And it's called Task to Sim, towards effective pre-training and transfer from synthetic data. So the idea here is we're going to simulate the pre-training data. Why simulate? Well, there are a couple of reasons. One is that, as I just told you, we want to have good control over our pre-training data. And one of the best ways to have control is if you're actually generating it, right? So here we can control all of these parameters. There are 8 binary parameters in our simulator that we can either vary or not vary. So one of them is the scale of the object, the texture of the object, the background, the amount of blurring, and so on, the lighting conditions, the camera angle. So there are all these simulation parameters that can be varied, and when you vary them, either turn them on or off, the data you generate will look differently. And so our hope is that we can learn to predict what are good simulation parameters to generate pre-training data for a particular downstream task. There are other reasons to do this, by the way, for example, copyright issues, or, even this problem of very large scale data from the web. You don't always know what's in it. You don't know what kind of harmful things might be in that data, maybe privacy violations. So simulation is actually potentially a good way to overcome all of those things. So, so our solution is task-to-sim, and I'll just give you a high-level quick overview here, and I'll refer you to the paper for the details. So we start with a task, which is a data set. We map it to an embedding using task-to-vec embeddings. And then that gets input into this model, our task-to-sim model, that then for a given task predicts what are the simulation parameters that we should use, right? So should we vary the pose, should we vary the background lighting, and so on. And then these parameters are given to the simulator. We use the TDW simulator that generates the data, and that's used to pre-train the classifier. And then we measure performance on we take that pre-trained model, we fine-tune it on the downstream task, and we measure its accuracy. Now, to learn how to predict good simulation parameters, we use a reward that consists of essentially k-nearest neighbor evaluation because it's fast. It's the fastest thing that we can think of, at least. And so that's the reward that's being used to update the parameters here. Okay, so does it work? I think it's promising. So here, again, the idea is to use task-to-sim to predict simulation parameters, generate a bunch of synthetic data, pre-train the classifier on that data, then fine-tune it on the downstream task. And so on the right here, you see the performance on unseen downstream tasks. So it means not the tasks that task-to-sim was trained on, but held out tasks. And here we're comparing for different ways of pre-training. The first one is pre-trained from scratch, and we compare linear probing with fine-tuning. Random, meaning just we vary these simulation parameters randomly, and then we pre-train on simulated data. The next one is domain randomization, which takes all the simulation parameters and varies all of them. So this is a pretty well-known method called domain randomization. And we're trying to do better than that by essentially predicting better parameters for the simulation, not just vary all of them. And then ImageNet is just pre-training on ImageNet, but with the caveat that we're using the same number of classes and the same size of pre-training data as our method is using here. So it's not the full size ImageNet. And then we compare with task-to-sim. So the interesting thing is that we can actually do a little bit better than ImageNet on these downstream tasks. Again, because we are tailoring that pre-training data to each task. So I think it's a promising approach potentially. All right, so that's all I wanted to cover today. Let me just summarize by telling you, first of all, if you don't remember anything else from my talk, I hope you remember this one point, which is don't just evaluate an IID test set. You can use, you can sample several out of distribution test sets from the existing data set, or you can use some of these benchmarks that I mentioned. But I just think that this is a bad idea. The second point that I talked about is all of these methods that align features, or they align the structure in pixel space or in some bridge domain. And these can be helpful on out of distribution data. It can be helpful to handle new domains and new distributions. But again, with this caveat that pre-training actually seems to matter more than the specific adaptation method that you're using. And here we saw that the larger the model, the better, the larger the data in general, the better, but not uniformly. Vision language pre-training sometimes hurts. Architecture probably matters also, and we need to look at this much more. And the final point is that perhaps we can bake the pre-training data, and this could be a potentially an interesting way to move forward that avoids some of the issues with real pre-training data. So that's it. In terms of kind of future work, I think it's very interesting to look at these advances that we're seeing in generative AI and generative image modeling. And I think some of those advances could potentially be quite useful for us to, create, again, better training data that helps our models generalize better to new distributions and new kinds of domains. So that's it. Thank you very much for your attention.
So we got a couple of questions in the app. Could transformer pre-training be combined with the bridge domain idea to improve bridge domain image representation?
Yes, so I think the bridge domain paper was not using transformers. And to me, it's still a open question if transformers are specifically better for generalization. I think it's likely that they are better at things like occlusions. But I think what matters more, at least based on our work, is the size of the model. But I think it's an interesting idea to combine those two.
Second question, is there a reason that the bridge domain remained in the one channel grayscale? Is it possible that bridge domain images could be multi-channel?
Yeah, I think that's a great point. I think it was just more or less convenience and kind of the first thing to try that we made this bridge domain be essentially two-channel edge versus background. I think adding color to it could be interesting, or making it 3D could be interesting, right? Because the objects have a 3D structure. But I just want to emphasize that the actual learning, the training of the representation happens on the original color images. It's not the bridge domain is only used for the alignment of the nearest neighbors.
And one more question. Does it make sense to explore the model parameter distribution and guide it somehow to better generalize across domains?
Interesting. So I guess model parameter distribution, I don't know if they mean kind of like in a Bayesian sense, a distribution over the actual model weights. I think there have been some Bayesian approaches to domain adaptation and generalization. So yes, I think that is a fruitful direction.
That's all the questions from the app. Any in-person questions from the audience? A couple of microphones. Trying to go to the microphone. All right, Terry, you want to start?
So, please, one of the observations during the talk was the transformers work for some and not for others. It works for some, right? In fact, do you see any potential that the issues that come with a fine-grained task, lots of small things where attention might really matter? Or if you may shift the document class, you can't figure out what to focus attention on, so that other fine-grained tasks might be a place to look at where transformers will help.
Yeah, so I don't want to give the impression transformers don't work for Cub, but they don't work as well. Or actually CNNs work slightly better, which surprised me because I was expecting that transformers going to be better on everything. And I think that there could be something in the architecture, right? That CNNs have this built-in invariance to the position of the feature in the image, and some invariance to small rotations and things like that. So it's possible that that is what's helping the CNN to generalize better on Cub. Yeah, but I'm not fully sure. Like, I think we need some more experiments to dig into that.
Yeah, I have a question. Thank you for the great talk. And I have a question about the last word you presented. I have a question about, let's say, because you incorporate in some sense knowledge about the new family domain. I would say the whole distribution of the domain for creating the pre-training data. Even just breaking the standard rule that you just don't know what the next data are coming to? Because in some sense, you are just looking at the distribution and saying that, hey, it's looking like this, so I can just move my model into this point of the space. But for me, it's weird because for the, let's say, cross-domain adaptation, I suppose that you don't know what the next data like in meta learning or continuous learning testing are coming.
Thanks for the question. Yeah, so I agree that this isn't exactly a domain generalization approach because we're giving it the actual data with labels. The generalization would come possibly later on when we're now like we're observing the same task, but in a new distribution. And we actually didn't evaluate that yet with this approach. But I do think that it's possible that for like, if you know that you have a particular task that is just not a good fit for web data, then it's possible that you could also kind of do something at the pre-training stage and you can generate some simulated data that helps you generalize on that task just by incorporating some maybe even prior knowledge over your task. And again, like this, I wouldn't recommend this for, you know, cats and dogs and these things that you can find online. But maybe you have a more kind of like satellite data or some other task where it's hard to learn that from all the web data, and you can use some insight to instead simulate kind of different domains for training as well. We're not doing that yet here.
Okay,
I have one question. I was like, for image data, where you use image made or where AI is used in different scenarios for getting down model. But what about domain efficient in sensor data, like LiDAR, radar data, or different kind of sensors? How we can get into type of models? So, is it possible to generate getting data for those image set of sensor data?
So by other sensors, you mean like depth?
Yeah, there's 3D LiDAR, point LiDAR.
And you're talking about adapting from RGB to these other sensors?
Yeah.
Yeah, so there are a couple of ways to approach that. One is if you have some label pairs. For example, you have RGB plus LiDAR for the same scene. You can actually train a supervised translation. And this is similar to image translation. Like if you have label pairs of sketches and real photos, you could train a supervised model that can translate between them. So I think that could be a good approach if you have that pair training data. If you don't have the pair training data, then you could do the kind of unpaired translation that also either in the input space or maybe in feature space. So, you know, a lot of the methods that I talked about would apply here as well. Yep.
So one of your conclusions was that the pre-training matter more than adaptation, but generally, I think it's reasonable to expect that the stronger pre-training and stronger model will have better generalization. So we probably have smaller than the gap too. So we see at some point that we could have like really good, really generalized models that kind of have minimal domain gap. So we should just like cross domain adaptation altogether and focus on pre-training or domain generalization.
Right, so I think your question is like, do I predict that we will drop post pre-training methods and just focus on or during pre-training? Yeah, I don't know. I think that's a great question. That's kind of what I have been wondering too. And, you know, it kind of in the limit, if you take it to the limit, like if you can pre-train on everything in the world, then you've seen all domains and you should be able to generalize by interpolation essentially. But I also think there are downsides there, right? Because the more data you're pre-training on, the longer it takes. So, and the cost, like some of the models that we have today, like Clip, for example, I can't afford to train one of those models. I don't know not too many people can afford to train one of these models. So I think that cost cannot really be ignored. I think we are going to have to eventually either figure out how to do pre-training with less data, but that still generalizes, maybe better coverage over different domains, or maybe some better kind of pre-training methods that build in some invariance. But yeah, I think maybe a combination of approaches is what will be eventually needed, but it's a very good question. I think it's an open question. Mhm. What's the question here?
So there's like in recent years, there were a lot of statements regarding test time training. And we should say very close the line between test time training and implementation.
Sorry, I didn't hear the question, but about test time training?
So they were like, where do you draw the line between test time training and implementation?
Oh, test time training, and I see. Yeah, there are a lot of, that's a good question. There are a lot of similarities. Also between domain adaptation and semi-supervised learning, or online semi-supervised learning. Where I would draw the line is essentially like, what about the distribution, right? Is the distribution the same or not? So if you're doing test time training on the same distribution as the training data, then that's not domain adaptation. But if you're doing test time training and the distribution is changing, then that has the flavor of domain adaptation. So I would call that domain adaptation.
I think we are over time, but let's thank Kate again, and I'm sure she'll be around to answer more questions.